Hello, everybody. Welcome to day two of SDEV 248. Got quite a bit to go over today, getting started on things. I filled up a full page of things that I'd like to get done today. I don't know if we'll get all the way through it, but we'll try. Uh, get all the way through it and still have time in our schedule block to actively apply this stuff and get some practice with it. It's a very active subject we learn by doing. Just a reminder, as we get started, there are two due dates on the discussion boards. The initial post is due by Thursday, and then the replies are due by the module due date. That way there's plenty of time for everybody to reply to stuff. Right? I'm sure most of us have seen those classes before where you might post your discussion board early in the week and none of your classmates post until like the day it's actually due, so there's never a chance to apply. So there are two due dates. If your initial post isn't Thursday at midnight, if your initial post isn't in by midnight on Thursday, then there'll be a small late penalty on that. So keep an eye on those. So that was the only reminder at this point. There's a couple things we want to talk about, make some notes on the board before we get started into the actual topics for today, because we're going to need them when we go to program our example here in a few minutes. You've probably seen them some before. So first thing is a little bit about vectors, just very quick coverage, making sure the computer is going to handle most of the processing. Really what a vector is it's a value that can't be expressed in a single number. A value, I'll write it that way, that cannot, whoops, let me try to write it a little clearer. Cannot be expressed as a single number. Means it's numbers go together, but we have to work with them as individual numbers, but we can't really describe the thing we're talking about without the multiple numbers all being there together. For movement, well, we're going to do quite a bit in video games, obviously. We usually talk about magnitude and direction. So how long is it? Good way to think about that is like a right triangle. We take the two legs of the right triangle, the hypotenuse would be the vector. So instead of just going over and up, how far do we go down the straight line and at what angle? But that's not the only situation for it. Colors are another one, an important one to note. We're using Godot for our examples, and Godot has this object called color, which is really just a vector. But a lot of our other game engines, a color is just assigned a vector 3 or vector 4, depending on if it has the transparency values. Because it's just three numbers. We need all three numbers, red, green, and blue, in order to describe what color we want. So we can't describe it as a single number. It takes three to describe color. Same thing with direction, magnitude and direction. I'll quickly draw something that looks like the state of Indiana here. There we go. So I'm down here in Sellersburg, right by Louisville, Kentucky, suburb of Louisville, Kentucky, for those who don't know where it is. So if we say travel for an hour, that's going to get us we know about how far we're going to go, right? but that's not enough information to say where we're going. Right? I mean, if I travel from Sellersburg in an hour for an hour, or I probably shouldn't use time, there's different roads, 30 miles, right? There's this circle that I could cover in that 30 miles. So to actually describe destination, we need both that the magnitude of 30 miles and the direction. So if I was to leave Sellersburg and go northeast for 30 miles, that would put me in a different location than if I was to leave Sellersburg and go straight south for 30 miles. We need both values to accurately describe the movement.
And,
What's that, Josh?
And I believe the walls in the maps for Doom and similar games were made using vectors as well, right?
Yes. Everything the computer does is a vector. So computers only do linear algebra, it's just all in the background. But for game development, we have to work with them vectors in the foreground. Or remember those graphics that we were looking at, and I was saying these are the ones we should probably lean towards, the scalable vector graphics. Vectors right there in the name. So it's an important concept. The computer is going to do the calculations for us. We just really need to know when to work with vectors. So a couple of things about some math stuff. For writing them on a board, I'm going to write vectors in a column style. So everybody's had elementary algebra, right? Like the 8th grade or so, where we first see the coordinate plane, and we learn about points. So maybe one point is 3 units over and 4 units up. And that gives us enough information to describe that spot. But it's locked in place. That point is only 3 units over and 4 units up. There's no other alternative. One way to think about vectors is you could think about a vector as the arrow that starts at the origin and goes to that point. I'm going to write it like this: 3, 4 with square brackets. So the vector that goes 3 units over and 4 units up. And one thing about this is we can move that anywhere we want, right? That arrow, if we started here and went 3 units over and 4 units up, we still have the same vector. It's just in a different location. We can come way down here. Start here, go 3 units over, 4 units up. I'm trying to draw them similar. Might be getting a little off, but there's it's still the arrow that points 3 units over and 4 units up, because we could turn that into like a rectangle. And then our X and Y components are separate. We work with them individually, but what we really care about is what would be the hypotenuse of that triangle. It gives us a lot more information. So as far as movement, the magnitude and direction, this one has an odd thing, but it's going 5 units at 36 point something degrees. Is an irrational number on that particular one. Probably could have picked a different one for starting. Oh, 2, 2. I'll do that in green. So like the vector 2, 2, the one that goes 2 units over and 2 units up, it's a slightly different direction. Coming off at a different angle. That one's going to be 45 degrees. So the picture's a little bit inaccurate here somewhere. The basic idea of a vector, think about it that way. And remember, we looked at that color wheel for HSV or HSL or HSB. When we get very technical, the L, B, and B is different in those coloring things, but in general, it kind of means the same thing. You can think of that pointing an arrow from the center, pointing to a different spot on that wheel. So that's where color thinking of color as a vector. Two important things. We can add vectors together, add and subtract. And when we add them, the like components stay together. So both of these have an X and a Y component. So if we added them together, we'd add up the X components and add up the Y components, and we get a new vector, which adding them together is kind of like drawing them in a different place. So instead of drawing that there, I'm going to come to the end of the first vector, 3 units over, 4 units up, and then I'll do another one that comes 2 units over and 2 units up. And in the end, we get something that's 5 units over and 6 units up. So the same as if we would have just started there and cut that straight line through to the end. We can also scale them. Here in blue, I'll do 2 times that 2 vector. And when we scale things, that scalar value is just a regular number out front for multiplying, is going to multiply by each component. So that would give us the 4, 4 vector. And negative numbers just go in the opposite direction. If we took -1 times this 3, 4 vector, we'd get -3, -4. So that's thing going 3 units over, 4 units down. So it's just the opposite direction of that original vector. So negative is just the opposite direction. Think about the XY plane. Breaking it down to a right triangle works because we learned the Pythagorean theorem at an early age, right? A squared plus B squared equals C squared. Equals C squared, or since we're in a programming class, right, we probably want this C equals the square root of A squared plus B squared. Everybody's know how, see how I got there? Pythagorean theorem, A squared plus B squared equals C squared. What we didn't learn way back in elementary school is this applies to no matter how many dimensions we have. So when we get to 3-dimensional stuff, X, Y, and Z, we just have another thing to add to our sum here. C squared equals, I guess, D squared in this case. But since this is programming, we probably want it in the form that we can actually program it in, because computers can't do one equation that has 2 answers. That would cause all kinds of problems. Or 3-dimensional space with time, and then we'd have that another factor there. So no matter how many dimensions we have, the Pythagorean theorem still applies. Very, very useful for vectors. We just need to kind of know when to use them. So think about that arrow. Instead of a point in space, maybe start by thinking about the point you want your character to be at a couple frames from now. And then the arrow that goes from where the character is now to that point in space. Next week, the reading assignment is about vectors, and it is the Godot introduction to vector stuff. It's not the entire section. There's just like 4 or 5 subsections to read in that, and then some stuff to answer. But we just want the intuitive sense of vectors, have an idea of when we want to use them and how to use them. With color, it's important to note that Godot, they went ahead and created an object called color that is just a vector 3, takes in 3 numbers. But a lot of our game engines and shaders in Godot, when we get to that later, a color is just assign a new instance of a vector 3, or a vector 4 if we have the transparency and opaqueness value in there. we don't need to get too in-depth with vectors right now. We're gonna see more next week, but it's gonna show up in today's example here in about 20 minutes, so I want to talk about that. Is it okay if I erase this? Everybody get that? That's taking notes. I'll pause for one more second so you can take a picture. All right. For those who haven't had me in class before, I always try to make sure it's okay to erase the board. Because I remember in many classes myself sitting there trying to keep up with notes, and then suddenly the board would get erased. Or even worse, sometimes the lecture would continue while the board was being erased, so there was always a missing section from the notes. One other thing we're going to see the first view of in our first example here today. Some stuff with Newtonian physics. Just because of how our society is, I have a feeling everybody's heard Newton's first law, right? An object in motion will stay in motion until acted on by an outside force. That's an important one. If our game objects don't do that, it doesn't look right. Right? If we let go of the key and everything suddenly comes to a stop, that just doesn't feel right for how stuff moves. We know there's friction, or at least a simulated friction under a character's speed. So we know when we let go of the button, that friction should slow the character down to a stop. If they're already moving, because if we're moving and it's come to a sudden stop, we're going to fall over. So awareness of that. Newton's second law. Yes. Did you say something? Oh, I'll write it out in words. Force equals mass times acceleration. This is an important one when we're programming. Again, the computer is going to handle the calculations for us. So we don't have to, we just have to kind of know what, that we want to apply a force, because that's how we move things in the real world, right? Our cars are a good example. The car moves because we apply, the tires apply a force on the road, and then the road applies an equal and opposite force backwards on the tires to push them forward. That's the Newton's third law, but it all revolves around the second one law here. We don't change the mass of the car. Right? The mass of the car is whatever they put together in the factory, and then the people sitting in it. So that's always going to be constant. We control the car by accelerating. Or a brake. We either have the accelerator pedal for a positive acceleration, or the brake for a negative acceleration. So we're speeding up and slowing down the car. So to control our car, we apply a force to the road. And to turn the car, we just angle the wheels so that they're no longer going straight, and then we get angular velocity, which applies a force to make it go a different direction. But this is how we control things in the real world, right? To move this pen up here and write stuff on the board, I'm using my arm to apply a force to control where it is. Always with an acceleration, because it's sitting perfectly still right now. So its velocity is zero. So it would always be zero unless there was an acceleration. Newton's first law. An object at rest, I said it in the terms of motion, an object at rest will stay at rest unless acted on by an outside force. So, except what we really control to get good simulation controlled simulated movement in a video game is we want to control the acceleration in order to adjust the forces applied to all the things so they behave in a realistic manner. Or it doesn't necessarily have to be realistic. We can make up new laws of physics as long as they're consistent. The player will be able to work with them. Force is instantaneous, though. So it's good for theoretical calculations. But really what we need is impulse. Impulse is force over time. Force spread out over time. So good example of the difference between impulse and force. You think of a car heading down the road at some velocity, and it's going to come to a stop. There's a couple ways that it could come to a stop. Let's do the non-controlled one, right? One of them is we could hit a brick wall. That's going to stop a car, right? Very, very quick. Our time interval is basically nothing. So Greek letter delta means change. So change in time is a time interval. Our time interval is basically nothing. So that's just the regular force applied. It takes us moving at a constant speed. It takes a certain amount to get that speed down to zero. But what changes is how much time. Because if we, instead of hitting a brick wall, hit a row of bushes, like running into a row of bushes is also going to stop the car. And just because it was a car moving at a certain velocity, it's going to take the same amount of force to stop it. But when it's applied by a whole bunch of bushes, spread out over a couple seconds, or well, depending on how fast the car's going, it might be spread out over a second. It's a lot different than hitting that brick wall, right? This one's going to destroy the car, and then this one applies the same amount of force to stop it, and it's probably going to scratch the paint a little. So impulse, time's involved. So we want to work with impulse. That's an important thing. So more to talk about with Newtonian physics, but those are going to show up in our example for today. Let's start with some coding stuff. That's the fun part, right? So has everybody in here seen Godot before? We just switched last fall from the statewide just switched from using Unity to Godot last fall. Unity was very problematic. And, yeah, so the Ivy Online statewide shell, the committee got together and looked at some stuff and decided, okay, we need to just go with something that's going to be easy to work with. To switch to Godot. So some of y'all might have seen Unity before. There's a lot of things that are similar, but some things that are different. For those who saw it in the 148 class, we're using character body 2D, okay, or 3D. We haven't. That's one nice thing about Godot is 2D and 3D are treated exactly the same. The nodes all have the same names, all that stuff. They're all same names, same parameters, just a difference in the number of dimensions in them. Whereas some of our game engines, it's like an entirely different game engine we have to learn whenever we switch between 2D and 3D. Those who worked with Unity know how that have experienced that one. Also, Unity has a character body. Character body is kind of a special thing. It's set up and customized to be a controllable player controllable character. Not all of our game engines have those. And this isn't the class in Godot. We're just using Godot for our example. All of our game engines do have what's called a rigid body, a static body, and a kinematic body. So those are the three we really want to use to make sure we're generalizing this. Because even the different engines that would all have a character body, they might not, they're not the same. They're customized differently, so we have to relearn that anyway. A static body is the things, the objects that do not change in space. They're like platforms in a platformer game. That's kind of what our example is going to be. When you see it, it seems odd to call it a platformer, but every platform's there that just hang out in space, and our character stands on those. And other than the fact that gravity doesn't pull them down, all the laws of physics do apply to them. A rigid body is one that the laws of physics apply. All of the laws of physics from the real world are already programmed into it. We're gonna set up a platform, a static body, tell the computer our character image as is a rigid body, and gravity is just gonna pull it down, land on the thing, and bounce around, and all the laws of physics apply automatically. All of our game engines have the rigid bodies. Kinematic bodies we'll talk about soon. Those are ones that we control through code, more through code than not player input. Rigid bodies can also be used that way. I very rarely use kinematic bodies. I just use rigid bodies myself, but in week 3 or 4 reading assignment, you'll read through and see the technical difference between them, but they can also be kind of used fairly interchangeably. So when we make our games, we want to use rigid bodies. And that way we're controlling physics, and in here we're generalizing the knowledge so that what we learn using Godot for an example applies to every game engine we might sit down at. And we get a lot more realism when we use the piece that is set up to just respond to is set up to just react and respond to the laws of physics naturally, as opposed to something where we have to code most of the spots and the laws of physics are slightly altered to make it easier for us to write the code for the player. So I'm going to call this rigid body 1 for an example, and create a new project in compatibility mode. What we're building up to towards the end of the semester, we want to have HTML exports, the web page exports. So we'll probably be using compatibility mode on all of our stuff. We're going to create that. Let's just do a 2D one. That'll work. So I'm going to set a new node for 2D scene and immediately, so we don't get confused on names. So this will just be our little world. This is a small example, so I'm just going to create a quick one. Maybe just use the Godot icon for images. First thing we need is a platform. So if we start searching for body, you'll see all of them we have. We have a static body, rigid body. Those are 2 we can count on being available in every single one of our game engines. So those are the ones we want to use to make sure we generalize this knowledge. An animatable body is available in quite a few. That's a static body that can be moved. So we can write some code to make that move. So like platforms that behave like platforms at first, but then fall away after a second or so. I think everybody's seen those in platform games. Character body is a unique one. Only about half of our major game engines have those, and they are different in every single major game engine, so it doesn't generalize well. In 3D, there's also notice there's also a vehicle body in 3D, which can be useful for making racing games or just having some sort of vehicle into your car. It has all the physics as they would apply to a car already built into the node. So for platform, we just want static body 2D. And there's our logic. That's where our logic for it's going to go. Platform doesn't have a whole lot of logic. It just sits there in space. And we need the other 2 components are graphical and physical. So the physical, the thing we absolutely have to have from the physics engine is the shape of it. the boundary where the laws of physics will happen. So if you search for a collision shape 2D, and then we also need the graphical component. So we search for a sprite 2D. This is just a quick example. So I'm going to use the icon, the Godot robot icon. I'm just going to drag that over and drop it in the spot that says texture. And then maybe resize it so that it's like platform size. Something like that. Since that is a child of the static body, its position is given relative to the static body. So we want to come in here and set our transform position back to 0, 0. That way, when we want to move the logical body around and just have the graphics follow along. Our collision shape, need something in there for that. It's just a square, so I'll just grab the square shape. Use the arrow tool here to surround this platform. That'll work. So now we have our logical body, our physical body, and the graphical body all built into one. So I can go to the parent one, the thing that's actually the platform. I can spell. There we go. Our platform, and then go to the move tool. I'm just going to copy it. I'll hit copy and paste. Notice when I pasted it, it indented a little bit more. So it's like it made it a child of that. So there's a couple ways to deal with it. What I usually do whenever it's indented too far is I'll just grab the parent and drag it up to the level that it needs to be at. So now we have two platforms. If I scroll out a little, notice that it put it way down here because it set it as a child of that first platform, and the position was relative to that. So I'll move it up here, and in the transform data, I'm going to come in and angle this platform somehow. Something like that'll work for our example. So one of them's flat, the other one's angled. Right, it's come down just a little. Then we can make a player real quick. So I'm making, and like we just talked about, at least one person that's came in since talked about it. We have character body, which has a lot of pre-built things for using a controlled character, but we don't have those in all of our game engines. And this class isn't on Godot. We want to generalize things so we can use it all everywhere. What we always have is so we want to put in a rigid body 2D and start getting practice using these because that's all of the laws of physics already built into it. So that'll be our logical body. We'll attach the script to that. I'll go ahead and call this, rename it player. That way we can keep track of things. Those platforms are good, so I can collapse them and get them out of the way. So logical body, then we need the physical body, which is going to be the collision shape. And then we need the graphical body, which I'll just put as sprite 2D on there. And again, I'll just grab the icon, the Godot logo, and drag it over to this texture field in the inspector. Oops, dropped in the wrong spot. Back, and So maybe make that a little smaller. We go to the scale tool. I'll just go to here. At first, when we start scaling things, the ratios are locked. Oh, it's not locked for some reason. They're usually locked together, so make sure you unlink them. Now we can change the aspect ratio, so like 0.2, 0.4. That'll probably work. In our collision shape, it's still rectangular, so we put on a rectangular collision. It was mentioned at least briefly the other day, we only need 4 numbers, 2 pairs, 2 opposite corners tell us enough, all the information we need to know about a rectangle. So if a rectangle will work for our collision shape, that's obviously a lot less data that has to be processed. And then I'll go to the move tool, kind of put this into a starting spot where it's going to fall down on that first platform. If anybody's on a laptop and doesn't have a regular mouse like me today, because I forgot to bring it in here with me, if you hold control, that does your panning. If you hold control and scroll on your mouse pad, and if you just scroll the mouse pad, that does your zoom in and out. I'm going to go ahead and save this as world. So this is just sort of the first introduction, right? We want to use the rigid bodies. Class has simulation right in the name, so we want to make sure we're applying physics correctly. So if I go ahead and run this, and see, just because it's a rigid body, the laws of physics include gravity, so it's automatically going to pull it down and land on the platform. And that's starting to weird spot. Pull that down. If I start it here, again, gravity is going to pull it down, but something different is going to happen, right? Very different than the first thing. So you can see the laws of physics applying, pulling, and moving it around. That is one that can be a little tricky. Everybody in here has been walking for a while, right? And you probably don't remember how hard it was for you to learn to walk to begin with, but babies learn really, really quick, right? When we're born, we really, really absorb information super quick, and then every day of our life that gets a little bit slower and slower and slower. So when you're primed for absorbing new information, it probably took what, 1.5 years to learn to walk. Probably still falling down for a while up into your teenage years. The human body is a terribly off balance thing. Our center of gravity is in a weird spot. Don't notice it, but our ab muscles are constantly doing stuff, constantly making adjustments. And when we try to code it, a human body is terribly off balance. That's why some of our game engines have that character body, because they remove some of the laws of physics, because the human shaped body is very, very difficult to code if you don't start restricting those full laws of physics. And like how it takes all of us 1.5 years to learn to walk. So you can see different things happening there. Let's move this over where it'll fall down on the flat one, and then we can see how to move this. All right, so it's standing up right now. So that's a good start. It's a square, or it's a rectangle. So the computer would have looked at that collision shape and been like, okay, this is a rectangle. There's nothing coded into the mass yet. We will do that later. Right? If we select it, notice there's all these things. So here's our mass. Where's the center of mass located at? How does inertia apply? Sort of linear velocity and dampening do we have? What's our angular velocity? So linear's moving forward, backward, moving in one direction, and angular is spinning. We'll see this as we go on. I just wanted to do an introduction to the first week, talking about the rigid body and static bodies, because this is how we want to code our games this semester. So it's gonna fall down and straight, so we'll probably start making this move. So I'm gonna add a new script. It inherits from rigid body, it has to do that, that's just sort of, object oriented stuff, we don't have a lot of notation, it's just automatic in game. So everything we work with is object oriented. And because of that, they cut out a lot of the notation because it's trivial and the computer can type that part since it's gonna go on every single thing. So you can see where whatever we write in this text file is extending this already existing script. So the other day there's two that we need. We need this ready function that returns void. And that's our initialization stuff. That runs one time whenever the object first appears in the game, or first appears on the scene. And then we have either process or physics process. Process will give us graphics priority. Physics process will give us physics priority, but nothing that fits in the time constraints of an 8-week-long class is going to get nearly big enough that the game engine has to choose priorities. But for each game, you might want to practice considering that is physics more accurate physics more important or accurate graphics more important? Because the game engine will choose. So I'll do a physics process because we're talking about that. Takes in this number delta, which we'll talk about soon, and returns void. So our syntax for creating a new function. Not really any initialization. This is just a very quick introduction to rigid body. Our first look at it. So we don't need it. The initialization is just what's already built into the rigid body. All the laws of physics apply, basically. So down here, we want to start doing some stuff. We need inputs. Everybody see input manager in the previous class, or I think it was on this week's reading assignment, right? So we'll go to project and project settings, and here's where we control all the stuff about our project. We go to input map, the second tab over. There's a bunch of inputs already built in for us, but they have really odd names. If we look at them, right, UI accept, UI select, probably not the way we would name our variables in our scripts. So we want to set things up with names that make sense to us. So how many ways can a platform move? It can go forward. Go here where it says add new option. Just type the name you want to use and hit enter. You can go backward or it can jump. That's gonna be our control. And then over here on the right hand side, this little plus sign. This is how we add controls, add actually inputs to that number. So see right now it says it's listening. So all we have to do is hit the button we want. So moving forward would probably be the D key. And this one confuses me all the time because I always want to hit D and then enter. But notice we hit enter, it's still listening. So it switches that. So hit D. And then you have to click OK. Oh, it's just gonna listen for the other event. I guess we can also do the right arrow on the keyboard. Or playing a little ahead, if we go to joypad axes, use the left stick on the PlayStation control. That's an easy one to move. So left stick push to the right will move us forward, and yeah, that one will set up for different devices. So move backwards, probably the A key. Some people might like using arrows, so go ahead and set the left arrow for backwards. And again, if some people might plug up a better controller and just use that, so we want to have that set up for them too. So maybe the left joystick push to the left also moves backwards. Jump. I'll put it on the space bar and joypad buttons. Yeah, the cross button on the PlayStation, A button on the Xbox, Nintendo B. Those sound like jump controls. So I'll just choose that. And again, it's listening to events. So if you had a PlayStation controller with a USB port, you just plug that up and click that, and it's going to hear program, and it's going to choose that button from this list, just like it does from the keyboard. I don't have one of those today, so I have to choose it from the list. That looks like some good input for the game, right? Should cover most players. Yeah, and it automatically saves. So anytime you change settings, just hit the close button. There's a couple things when we do editor settings that we do actually have to hit save and then restart the editor. But for project settings, it's just automatically saving all constantly. So now that we have those controls in there, we can come in here and start setting up our movement. Which again, character body makes it a little bit easier, but we don't always have character body in our game engines. And the game engines that do have character bodies are all different. So if we use that here in this class, we're not learning transferable skills. I'm guessing that a lot of you probably want to start using Unreal after class, right? That's the one to make games on. And yeah, statewide, we decided we're not going. On the SDEV committee decided we're not going to ask somebody to buy a $3,000 computer for one class. So that's yeah. So not using it in class. Some of y'all might want to go there, so we'll make sure we learn transferable skills. So rigid bodies, the laws of physics all apply. So we have to do our movement based off the laws of physics. So first off, I'm going to set up the selection structure for detecting the input. So it's input dot is, we can sit here on the list. Oh, there we go. Is that better on the screen? Did everybody see that okay? Actually, first off, I'm going to come way down here and just add some white space for scrolling. That way I can control where that's at on the screen. So we have an input object. It's an input manager object. And we have a couple ways to check our actions. Is action just pressed or released, or is action pressed and released? The just happens once, no matter how long we held it down, right? If we hold down the D key, that should move our character to the right, but it will only happen one time until we release that key and hit it again. Is action pressed happens over and over again every frame of the game while we're holding it down. So for movement, we probably want to be able to keep holding it. I'll check for forward movement. And I'm just going to put pass for now and type up the structure. If what's a good way to say this? The point I'm often making that class, the code needs to be in a certain order for the computer at the end, and that order is probably not the same as the order we think about it in. Over the years, I found it's a lot more productive to kind of bounce around your text file and put things together in the order you think about them in, and then just make sure it's in the order the computer needs it at the end. And look for patterns, try to make use of patterns when possible. I'll bring that up a few times. This one's not very long, so it's not much of a thing. So if we're not pressing forward, we could be pressing backwards. Is action pressed backward? Moving either left or right. Pass. And usually when I'm coding games, it's almost always ifs and else. There are very few situations that an else is acceptable. Because an else covers every other possible situation, right? There's a lot of those pre-programmed in inputs and things like that we wouldn't want to cover. So usually we avoid else's. But in this case, I think it would be because we're either pressing forward or backward, or we're not pressing them. There is a binary situation. So, because so many things can happen and go together, always make sure that all of your if, else, if stuff is definitively binary to everything else that can happen. Yeah. But it's almost always if, else blocks in the syntax, or here in C family, if, else, if, or whatever the syntax for the language is. And then that catch-all default thing, you often want to avoid those because that can lead to unintended consequences because there was another situation that you didn't realize the computer was monitoring when you put it together. And again, I'll just put pass for now, and then, right, so think about one thing at a time. Just think about the selection structure. Now we can come back in here and write what to do. Like the words. What you're going to do as you're studying and putting your games together is you're going to go search for things, right? You can go search for rigid body 2D and Godot. And always look at the official documentation first, because that's the user manual. That's always going to be up to date. And that's going to be the whole picture. Tutorials might be easier to follow, but by the nature of a tutorial, it's only the starting steps. That's what a tutorial is. It's never going to show you the entire picture. It's not going to show you the whole thing. The user manual does, but it might be a bit confusing at first. But always look here first. And when it doesn't make sense, then come back, then check out the tutorial. And don't use the tutorial to learn that one step. Use the tutorial to learn how to read the user manual. Okay, so learn what you need from the tutorial, come back here and then be like, oh, that's what they were talking about in this paragraph. That makes sense now. And then after you do that a few times, you'll be able to basically read the user manual and understand everything that's happening right now. Godot has a really, really good user manual if anybody's hopped into the reading already. So we have a bunch of properties here. Here's all the stuff we have. Angulars, rotational, and linears moving along. So velocity and damping, center of mass, all these properties. We get down in our methods, and we have things like this: add a constant central force, add a constant force, right? That's what we were talking about. That's what we were talking about in Newtonian physics earlier. But we quickly went to impulse, right? It takes a certain amount of force to stop a car moving at 50 miles an hour. And if we apply that force by a brick wall instantaneously, it's going to do a lot of damage. But if we apply that force over time by, like, say, hitting a row of bushes, it's probably barely going to scratch the paint on the car. So impulse is a better way to control it. So along with applying forces, those have impulses, and it's good documentation. They can read about them. It's very, very thorough. This is the one. This is the one I decided to use today. Let's apply a constant force. A constant force is applied to the body and keeps being applied over time. So it starts accelerating it. Right? Our object has a mass, it's preset at 1. Before long, we'll get into adjusting those more accurately. And the force is going to change that acceleration. An impulse is time independent. Applying an impulse every frame would result in a frame rate dependent force. It's an important note, but things like that are kind of confusing at first, right? So read through it, try to make sense of it the best you can, do research looking into things, but our description applies a directional impulse without affecting rotation. I think that's what we want for movement. Star Trek. That's a good one. They just straight called it impulse. Apply impulse goes in some direction. Of course, it starts it moving in some direction. Then Star Trek, they're in a spaceship. It's in space. There's nothing opposing it. So once they start moving in that direction, it's going to keep moving in that direction. So that's what we want. That's what we can use for our movement. So you want to look that up. So we are in our player object, which is inherits from rigid bodies. So we are inside the rigid body, so we can just do apply. Oops. Apply central force, central impulse. Yeah, I'll do a central impulse so that we're pushing at the middle of our character, not at the top. Because what's going to happen if we push at the top of the character, right? Same thing if we walk up and push somebody at the top of their body, it's going to throw off their balance. Or push at the bottom of the That's like the leg sweep in karate, right? Go down and kick somebody's feet in a different direction than where the rest of than where their center of mass is, and they're going to go flying. And here we need to apply some sort of vector. So which direction does that go in? If we're going forward, that's going to go in our X direction, right? I'm going to put a 1 there and a 0 in the Y. Oh, whoops, sorry. Vector 2 first. We need a 2-dimensional vector. Talked about those earlier. And we want to go in the X direction, but not in the Y if we push the forward button. How far do we go? Again, this is related to forces, right? And just like when we're driving a car, what we control is our acceleration. Either linear or angular acceleration when we turn the wheel. And then that creates forces that move the car in some direction or another. We want to think about that. Think about things like that. When you're driving around, think about how the forces are applied, because that's what you're going to want to program into your games. So let's set up an acceleration value. So our syntax, we have var, which just means we're going to create a variable, give it some sort of name, acceleration, then a colon, and then the type of data it is. This is a strictly typed language. It goes through basically goes through the C++ compiler, which is strictly typed language. And if we don't put the type in there, it goes in as variable type, which makes things considerably slower. So you always want to put your type in there, which can be inferred from the walrus operator. Right? I think everybody's probably seen the plus equals, minus equals, times equals. If we do the type operation and then the equal sign, it will automatically find the type. If we know it, it's I'm going to type in a number. Let's just try 15.0. I'm taking a guess. So if we push the forward button, then we can do acceleration in the X direction, nothing in the Y direction, and we should start moving in the X direction. All right, hang on. And our follow along examples will get faster soon. I bounce around a lot. So those who haven't had me in class before, I always like to start off kind of slow and we'll get faster as it progresses. Now if I push D, oh, it moved. It just kind of fell over. But, it did move in the right direction, it's just a little off balance. For that, that's one of the things that's going to be, uh, the difference between the rigid body where we have actual, all the laws of physics and the character body where things are constrained. We have to go set that constraint. So if we go to, deactivation in the inspector panel, and again, that it's going to be in the inspector panel on the rigid body in all of our game engines, just in a slightly different spot, maybe with a different label. But there is going to be a way that we can lock the rotation so it no longer spins. And in 3D, we can lock rotation around. We choose which axes it locks rotation around. So if you just hit lock rotation, it's not going to be able to spin and fall over again. Now we should move. Oh, I don't know what's moving. I hit this earlier when I had my example and I just talked about that thing. There's going to be friction between our character and the ground, right? And we haven't changed any default settings. So right now, everything has the same default settings. So um, applying a force, it's just pushing up against it and the friction's holding back. We'll get to that stuff later. So what I did when I was getting ready is I just put up by 0.5. Gravity is going to catch that pretty quickly. It's going to start it moving up so that it, a way to suddenly cut the friction out and we can start moving. I did that when getting ready for today and forgot about it and just went right back to the 0. Why is that not moving? Let me try unlocking that. I'm going to unlock that and lights and labels.
Mine didn't even fall over.
See if I'm missing something for my example. When I was getting ready, I also had this. Whoops. Somehow went into insert mode. There we go. Also, I have the at export. What this does is it makes it visible in the inspector panel somewhere.
Might it be because physics material is empty?
No, physics material we'll get to before long. I accidentally changed something else. So I had that. That shouldn't make much of a difference. And then for the other way, we just need to go in the negative direction. I'll go ahead and write all the code out in the example instead of building up to it. And then here, when we let go of it, we want a vector that doesn't no longer applies force. There's one built in. So if we do vector 2.0 in all caps, that's the 0, 0 vector. Is action brisk, forward, backward. I did call them the right thing, right? Forward, backward, and jump. So yeah. I had to have made a typo from when I was getting ready earlier and I don't see it. Let me make sure it's the right thing. Oh, you haven't seen this before? If you hold control and click on it. This also goes to the user manual. So hold control and click on the built-in functions. Try force. See what, if that's making a difference. Now force isn't even moving it. So I think I might have accidentally clicked on a box somewhere. Is anybody's moving from this?
Moving at all?
It's just falling over, right?
Not even that for me. But mine's also just a square, it's not tall, so I don't know if that would have any effect on it.
Those notes are like in the way and not helpful apparently. Maybe there's just not enough acceleration to overcome the friction. I'll try a bigger acceleration.
Yeah, how it works. It just need more acceleration.
Right, so physics get in our way. Got friction. And then a jump is gonna be a similar thing. So just hone in on a number, because obviously we're gonna probably get way too big of a number eventually. Or before long. So it's way too big. And remember, that's gonna be an acceleration, it's gonna keep applying it. So we probably also want to set some sort of max speed. And that we can hone in on. We'll see more of that later. Let's just do the jump real quick before break. Similar thing. We want to check our input manager. Only jump, we're only going to do once. So we'll just do that. It use the just press. Is action just pressed? And then no matter how long we hold it down, it's only going to count for the very first time. And we can apply a central impulse, which needs to know which direction does that vector to go in. It's not going to change the x direction. Oh, it's already racing board. Remember when we were talking about vectors earlier, we can add vectors. So if it's already moving, this is going to add to that previous vector. So not going to add anything to the x direction, but it should add something in the y direction. I don't know. I'll try 30 here. Let's see what 30 does. Actually, should probably make a variable jump acceleration. Copy that. And again, if we go add export, it's going to add it over to our inspector panel so we can just type the number there. I'll try 30, see what that looks like. Whoops, what did I just do? Now it moves back and forth and has that rotation lock. What number did that take into? Oh, okay. I just made a silly little mistake. Which direction is positive in the Y? Anybody know? I think here. Oh, it's really, really small. If you look at the ruler, you can see it. 0 is up at the top, and then it goes down. So by putting positive 30 there, that's trying to push the player into the platform. So we want a negative 30. Should be going the opposite way of gravity.
Except you have to set it to a really big number, otherwise it just barely jumps.
Yes. Let's try 300. That works. Not enough to get to our other platform, but sometimes the first number is just a guess, and then after that you can kind of hone in on what you need. Okay, 900 is way too big. Let's try 500. Because for a platformer, we should probably be barely making some of our jumps, right? Ones on level 1 be nice and easy. Okay, this is interesting. So I'm pushing the D key, and I can't bulk up that, right? Because to go against gravity takes more force. But if I jump up here, when I push the A key, it goes a long way, so it just starts sliding. So that's how we're going to want to program our games this semester, using the rigid bodies and the laws of physics. It's going to take some practice, but we get a lot more realism. Your games have much better control as we the players will feel much more in control of what the characters are doing than having just some of the hard coding the character. Take some game practice, but we'll see it over and over again. That's the simulation part of what's in the course name. Any questions about that? See anything popping up in the chat? If there's no questions, it's probably a good time for a break. 10 minutes sound good to everybody?
So what's interesting is it seems it can't jump if it's moving. It has to be standing still and then jump.
We will get to that. So this is just sort of introducing it. We're going to see more stuff, play around with it a little. I'll put my code back on the screen during break, Josh, and see if you can figure anything out.
I have the same code. It's just
okay. Well, let's take a 10-minute break then. Let's sip a coffee. So I will see you all in. Let's see. This clock says 2:15. We'll get back to it at 2:25.